This lecture on data communications and network 1 class is on wide area network, chapter 8. Okay, and this is lecture 15. Okay, so part 1 of wide area network. Okay, so there are two ways, okay, two basic ways to share a network. The first one is switching network. The second one is broadcast networks, okay. Wide area network is a switching network, and the broadcast network is usually used in LAN, okay. Before we get into wide area network, we talk a little bit about broadcast network. The broadcast network do not need switching, okay. So, and its broadcasting means that everyone gets the information. So you have to make sure that only one sender sends at the same time. If many senders send at the same time, they will collide to each other. The data will collide, and so the data will be lost, okay, due to the collision. So you must overcome the multi-access problem. So in LAN, the main problem is a multi-access problem, and another one is security. But for the wide area network, okay, there is no multi-access problem because we have switching to go to the correct destination. Let's look at an example of a switching network. A switching network may look like this, okay? So you have the ABCD, as the users, okay, of the network, and you have in the network there are switching nodes, okay? So there are also 1, 2, 3, 4, 5, 6, 7. They are the switching nodes. So if you want to go from A to B, okay, you can go like this. You can go like this, okay. If you go from A to D, you can go this way. Okay, so this is one way. And another way is that you can go this way. Okay, another way is that you can go this way. So there are many ways that you can go from A to D, okay. But if you only go to the switching node, that is in the connection, okay. That will go to the destination. If you use the blue, okay, the blue route, okay, it will visit the switching node 4, 5, and 3, okay, but it will not go to 1, 2, or 7 or 6, okay, so it will just go visit some of the switching node. So the other user in the system will not receive the data, okay, will not see the information or will not see the packet. Now, so this is suitable to transmit the data from source to destination. That is, there are multiple stations and the distance is usually long, okay? So that you go to only, you go directly to the destination, okay? You don't have to, so if you want to go to, for example, from Bangkok to Chiang Mai or something, okay? So that you can use the correct or the suitable intermediate node. Now, okay, this is not the mode. Transmission node, okay? The transmission node will switch. So this is transmission node, okay? So you will switch switching node. Okay, the switching node. So the switching node in the network, okay, will switch the incoming data to the appropriate route, okay, until it reaches the destination. Now, if we look at the type of the switching network, there are basically two main types, okay. The first one is circuit switching. The second one is packet switching. But the packet switching is also divided into two different subtypes, which is virtual circuit switching and datagram. Now let's look at an overview on the circuit switching. Circuit switching is a dedicated circuit, okay, and it has 3 steps in in the transmission of a packet. Okay, first you have to set up connection. Okay, second you do data transfer. Third you will end the connection. Okay, so this is similar to the HLC. Okay, that you have to have 3 phases. Okay, set up connection, data transfer, and end connection. The second one is a packet switching. The packet switching has no dedicated circuit. Okay, which means that the data assembles into packets and it will send. Dedicated circuit means that it is used for only that pair of users. No dedicated circuit means that the link, the part inside of the network are shared by many users. Okay, it's not assigned to a specific users for the sole use of some users. Okay, so in this case, data assembles into packet and packet is identified. Okay, with the destination. So it's like putting address. Okay, I want to send to Mr. A, something like that. So A is the destination address, or it may say, oh, take the bus number 1, okay, to go to that stop, something like that. So it will identify the path. Take the bus 1 for 5 stops. Okay, then you reach the destination. Now for the virtual circuit switching, okay, all of the packet will continue follow the same path. So you will set, for example, from node A to node B to node C to node D, okay, and that's the destination. So all of the packets, supposed to send 10 packets, all of the packets will follow the same path. And it still have the same 3 phases as the circuit switching, okay, set up, transfer, and end. However, the path is not dedicated to this pair of users. So I mean, everyone can share the path, okay, inside of network. So it's packet switching and not circuit switching. For the datagram, it's good that we don't need a setup phase, okay? So no setup, no end connection, just data transfer immediately. However, the packet, okay, the node has to be smart because the packet has to go on its own path. So every packet, okay, may go to a different path. So for example, from user number 1 to user number 2, okay, they may send 10 packets, but all these 10 packets may go to a different path. Okay, so this is so the node has to be smart because you have to decide which way for each of the packet to go. Okay, so this is good to send only like a piece of data. For example, you want to send in the real world, okay, and a mailman, okay, you want to send a packet or a letter, and it's only one piece, okay, then it's good to send like this, okay, with the address and then go there. For the circuit switching, okay, as I said, there's a dedicated path between 2 stations. So this part is for the sole use of this pair. So even though there is nothing to transmit at that time, no one else can use it because it's fixed for the transmission between user 1 to user 2. Okay, so it can be quite inefficient. We usually use mostly for voice traffic, okay, like the telephone system. In this case, you will set the connection and end connection. So there's delay in this phase, okay. In the setup connection, if it's a telephone system, so when you dial up, it's set up connection. When you hang up, there's end connection, okay. Now, when the connection is set up, the data transfer with a fixed data rate, okay. Which the fixed data rate are, so this is fixed. It's always sent at this data rate. And the only delay is propagation delay. So it is like the network is transferring to the user, which means that they have a link, direct link from user A to user B, for example, and it's like point-to-point link, okay? Because when after you connect, there's a direct link between them, and so it seems like there is no network, okay? But the network is into effect of when you try to set up the connection and end the connection. Okay. Now, so the voice traffic, okay, require constant transmission rate, right? So when you talk to someone, you want them to hear you as at the speed that you are talking, right? Not that the first word go very fast, the second word go very slow, okay? So it will feel like it will feel annoying, okay? So we want the delay to be small and fixed. So this can be done by circuit switching. So when you have telephone, okay, and this is your end office, so you make a connection, you see that there is input at this port, okay, and then output at another port, because this port is connected to the long distance office. In case you want to call a long distance number, okay, so you have to connect to the long distance office. But if you use, if you want to go to another area, okay, it will go out with a different port, okay, at the output. After the long distance, okay, so you have the connecting trunk and you have the intercity trunk. So this one will go to intercity, okay, go to the correct city. So it have to have a specific output, okay, output node, output port to go out, okay, and then supposed to go to another province, okay, in Chiang Mai, for example, and then the end office will go to the correct area, okay, and then to the destination, okay, have to go out this way to the destination. If the destination is the other person, okay, it have to connect to it may have to connect to the other output, okay, depend on the area that your user, your destination is in, okay. So after it's connected, you see that there is a direct line between the the sender and the receiver, okay, or the sender and the destination. There will be a direct line. So it seems like there is no network. That's why network is said to be transparent to the users. So if you want to talk to someone who are in เกษตรศาสตร์ for example, so you connect with the same, end office. But if you want to talk to someone outside, okay, outside จตุจักร maybe you have to go to the other, exchange box, okay, or exchange station. Now let's look at the circuit switching concept. There are two ways to do circuit switching. The first one is space division switching. The second one is time division switching. For the space division switching, it's like what I just showed you here, that it will go to the correct port, output port, okay. So it looks like this. So you have the input and the output doesn't have to be the same, okay. Suppose you have n inputs and m outputs, is okay. But usually they are the same input and output port, okay. And this is at the node inside of the network, okay. So you have to make a connection between the input and the output to the correct destination. For the non-blocking switch, the non-blocking switch means that you can send whenever you want, okay, and you can connect 100%, okay. There's no way you cannot connect to the other side, okay. In this case, mean that you can connect any input to any output simultaneously, okay, but you cannot connect to more than one output, okay. So it's like you talk, A want to talk to B, okay, and C want to talk to D. This is okay. But if A and B want to talk to C together, this is not okay. Okay, so not more than one output to the same output, and also okay, again, so we can, if you have A want to talk to B and C want to talk to D at the same time, this must be okay to be a non-blocking switch, okay. But no more than no more than one input, okay, to the same output, okay. So if A and D want to talk to C, this is not okay. But that is not what is done anyway. Now to be a non-blocking switch, we need to be able to arrange the input, okay, in any new order or in any permutation. For example, the user number one, okay, if you have n users, then user number one must be able to talk to any, okay, of the users, okay. Suppose you have like n input and n output, So the first user have to be able to connect to n outputs, okay? The second user can connect to n minus 1 output because the first user has connect to already one of the output already. So the second input can connect to any of the n minus 1 output, okay? And the third input can connect to the n minus 2 output. Therefore, the number of permutation that you need is n factorials, okay, like that. So if you don't have n factorial permutation, the switch have to be blocking switch. Now, what is a blocking switch? For the blocking switch, okay, you cannot connect any input to any output simultaneously, okay? Even though if you don't have to do it at the same time, okay, it's still okay. So you have to be able to connect all, like A want to talk to B, that's okay. A want to talk to C, okay. A want to take to D, is okay. B want to talk to C, B want to talk to A, want to talk to D, these are okay. Even with the blocking switch, okay, A can talk to anyone in the output, B can talk to anyone in the output, C can talk to anyone in the output. However, if A have talked to B already, sometimes C may not be able to talk to D, okay, at the same time. Even though D is not using the telephone, okay, C cannot talk to D because another pair is talking, okay. So when it's blocked, it's not blocked for all case, okay, just that some of the case is blocked, okay. And so A can talk to B, C cannot talk to D, but E can talk to F, okay, something like that, okay. So some of the connection will be blocked. This is called blocking switch. However, every one of them, if no one else is using, everyone can talk to anyone that is choose, okay. When in practice, we usually we use blocking switch, okay, to save the resource because you can make it to save, to save the cost, so you can use blocking switch. But we try to make it not block too much, okay, just block a little. Okay. So if you, sometimes when you call someone, okay, when you call someone and they say that they did not use the phone, okay, but you call but it's busy line, it is possible that it's busy at the switching node, okay, that is possible. Now let's look at the implementing of the space switch, space efficient switch, okay. The first one, easiest one is crossbar switch. This is a non-blocking switch, but it requires a lot of crossbar. It requires n square, okay, crossbar for n inputs and n outputs. So it's very expensive, okay, for a large switch. Suppose n equal to 10, 10 square is 100 already. So you have to have 100 switching point to support only 10 users, 10 input and 10 outputs. And if you have 1,000 users, you have to have 1 million, okay, 1,000 square is 1 million switching point in the switching node. And if a crossbar, even though it have a lot of like 1 million switching point, if one crossbar is not working, okay, there is no way to connect that input to that output at all, okay. Even though you have another almost 1 million switch available, you cannot connect if that crossbar cross point is not working, okay. You cannot connect like from A to B. So this is if sufficient use of cross point. Let's look at the case for the 10 to the 10 crossbar switch. Now, if we have okay, if we have something like this, and if I want to talk from A to B, I have to use this switch, only this switch, okay, to go from this to this, okay. I need to use only this switch. So if this switch is not working, there is no way, even though I have a lot of switch left, there is no way I can connect from A to B, okay. And if I want to send, for example, E to F, for example, I only have to use, I can only use this switching point, okay. So for the crossbar switch, there is a specific point that you have to use, and when A talk to B, okay, E can talk to F, no problem, because it's used different switching point, right? So this is non-blocking switch. So if, as an example, if we use 10 n equal to 10, okay, we have 100 cross point. If you connect all 10 inputs to all 10 outputs, okay, we use only 10 cross point, as I just showed you, okay. So one pair use only one cross point. So the maximum efficiency for this case is only 10%, which is really low. Now, to broadcast, okay, we can connect one input to many outputs, okay. So if you want to broadcast, you just one input and you switch for all of the output that you want to broadcast. The second case is the multi-stage switch. This case can be blocking or non-blocking, okay. We use fewer numbers of cross point than the crossbar switch, so this is cheaper. And it's like Lego, okay. We use a basic element of multi-stage switch. We have two types of it, okay. The first one is the connect first input to first output, second input to second output. The second one is the cross, okay. First input to second output and second input to the first output, okay. So you have inside of the connection is like that. When we draw, okay, to make it easy to see, okay, straight line and the cross line. Now, if you use 2 by 2 box, okay, as a minimum, okay, and will be a power of 2, right? So you have only 4 cross point inside of the 2 by 2 switch. Now, suppose n equal to 8, we will need instead of 64 cross point, okay, and with the one crossbar, we will use 3 stages, okay, log base 2 of 8. And we'll do something like this. So you see that the connection is kind of symmetry, okay? So the first one has to go to the upper line and the lower line, right? The first one has to go to upper line and lower line. The second box also has to go to upper, you know. This one is like divided by half. So one go to up, one go to down, one go to up, one go to down. And this in this side again, one go to up, one go to down, one go to up, one go to down. Okay. And then you divide it into 2 sets, okay? This one you divide again, okay? So you have up and down, okay? Up and down, okay? Again for this. So if you make this, you see that you have 8 inputs and 8 outputs, okay? And you can connect them together. For example, if you want to connect 1 to 6, for example, what do? 1 to 6, 6 is in the lower half, so you have to connect to the lower line, okay? And then lower half, right? So this one, you have to go like this. This one go like this. So if you make a connection like this, cross, you will go to 1 to 6, okay? Now, if you go 1 to 6 already, this is a blocking switch. So if you go 1 to 6 already, you cannot go 3 to 5, right? Because if you cannot go to 3 to 5 because this one is only cross, okay, so if it's cross, you have to cross like this, okay? So the cross means that this one can connect to only this block, right? It cannot connect to block of user 3, right? It cannot connect to block of user 3. Oh, sorry. 3 to 5 is okay. 3 to 5 is okay because you can go this way. 3 to 5 is okay because this is cross, but let's see what is not okay. So 3 to 5 is okay. This is okay. This is okay. So we already used this one, right? So this one has to go like this. So if you want to send 4, okay? If you want to send from 4 to 8, it's not okay because 4 has to go this way. If 4 go this way, okay, there's no way that it will go to the lower side. Okay, so 4 to 8, not possible. Okay, so 4 to 8 is not possible. When you get 1 to 6 and 3 to 5 already, 4 to 8 will not be possible because 4 can go to only 1, 2, 3, 4. Okay, so you can see that for the blocking switch, some of the pairs, okay, can happen at the same time, but some of the pairs cannot happen at the same time. Since you cannot send whatever you want at the same time, it's called blocking switch. Okay. Now, number of cross points in a multi-stage switch, okay, equal to the number of box in each stage multiplied by the number of stage, okay, multiplied by the number of cross points in the box. So you have how many box? You have 8 box here, okay, and how many stages? You have 3 stages. So you have total of 24 blocks, and each of the blocks have 4 cross points. So you multiply them, you get you can get 8 times 3, right? So 24 and times 4, okay. So so you have, in this case, you have 96, okay, cross point. But if you use a crossbar switch, you will have 64 cross point. Okay, so what I want to tell you is that if you use, small number of inputs, okay, the crossbar can use lower cross point numbers than the multi-stage switch. But if you use a large number of users, like 100 users, then the multi-switch will use fewer cross point than the crossbar switch. Okay, so this is example. Okay, so the formula for the number of cross points for multi-stage is 2 times n log base 2 of n. Now look at an example. If n equal to 1024, so this is the number of inputs and outputs. Okay, number of cross points in a crossbar equal to about 1 million. But the number of cross points in the multi-stage switch is 20,480 cross points. So this is much lower than 1 million cross point. Okay. Now, if you want the multi-stage switch to be non-blocking, okay, you have to use about twice as many cross points as the blocking multi-stage switch. So you just multiply. So the non-blocking multi-stage switch, okay, will require 2 times log base 2 of n minus 1. Okay, so this is the formula here. The non-blocking multi-stage is more complicated and have a long delay, okay, compared to the crossbar switch. If you look at this, you can see if you want it to be non-blocking, if you want 4 to 8, okay, you have to have other stage, so that this one can go down. Okay, so you have to have other more stage and this, so that this one go up and then it can go down, so it can go to the input to the output 8. Okay, that's why we require more stages. Okay, now let's look at the time division switching. In this case, the first one is TDM bus switching. In this case, if you remember, when you do the multiplexing of the TDM, time division multiplexing, okay, you turn it into a circle, right? So at the transmitter, you send in order, okay, so you turn in circle. But at the receiving end, if you can vary the order, if you switch based on varying the order, you can send the data from the first user to the maybe to second, third, or fourth users. Okay, you don't have to send the first user to the second to the first destination, because if you can vary the orders of the signal, of the input signals. Okay. Now the second one is time slot switching. In this case, we switch the data from slot number 1 to slot number 3. Okay. So if slot number 1 is related to this destination number 1, and time slot number 3 related to the destination number 3, it means that the user is sending the data to destination number 3, okay, by putting the data in the third slot. Let's look at an example. If you input to a node, okay, at time slot 4 in a TDM frame, time division multiplexing frame, then if the output is slot 10 in a frame, okay, so you have number 4, right? So you keep the data in the number 4 slot in the memory, and then when it goes to slot number 10, you just put the data from slot number 4 into that slot. This is how you change the data, change the slot, okay? How you do the switching. But if you want to put the data from the node 4 to the node 2, from slot 4 to slot 2, okay, you cannot do it in the same frame, okay? You have to put it in the second frame. This is okay because the slot number 2 belong to the destination number 2, right? So all slot number 2 in all frames is given to destination number 2, but this will have a delay more than maybe more than this one, because this one is in the same frame, okay? Okay, so it's possible that you have to suffer a delay up to about a frame length. Usually in many cases, okay, we do full duplex, okay, switching at the node, okay? So if user A and B want to interchange their data, okay, you can do it like this. You see that the input, okay, you have the input, okay, and input lines, and you multiplex, okay, into an input frame. So you have a time slot 0 to 7. You input to the time slot interchanger like this, okay, which has a buffer, okay, has a buffer, and this is the this have the inverse mapping table, okay. So the one on the left, the number on the left is the time slot, the input time slot, and the one in the table, okay, is the output time slot. So slot number 0, okay, input of slot number 0 will go to slot number 4. Input of slot number 1 will go to slot number 7. Okay, let's see what happened. Input of slot number 0 is on the leftmost slot of the frame, okay. When you go out, okay, you put slot number 0, data from slot number 0 to the 4th, okay, slot, because the slot is number 0, 1, 2, 3, 4, okay. So the fifth one is slot number 4, okay. And you can see that the input slot number 4 will go to slot number 0, so they interchange the data. User 1 and user 4 are talking to each other. So 1 send to 4, 4 send to 1, 0 send to 4, and 4 send to 0. So user number 0 and user number 4 interchanging the data. You can see that as here, input number 4 on the left, okay, slot number 4, output will go to slot number 0. So you see that the data of the first slot of the output frame is the data from slot number 4, something like this, okay? And you can see another pair is 1 to 7 and 7 to 1, okay? So slot at the output slot, the data of slot number input number 7 go to slot number 1, and the input of data input of slot number 1 go to slot number 7, okay? Then you go to the demultiplexing. Demultiplexing go in the same order, okay? However, the data of 4 will go to the first line. The data of 7 go to the second line. Okay, this is how they communicate with each other. The soft switch is not really a Newton, it's what we are using. Okay, it's a general purpose computer. Okay, running specialized software that turned into a smartphone switch. Okay, so you can kind of have like software, and then it switches to the appropriate destination. It's costless than traditional circuit switch. Okay, and it have more functionality than the traditional circuit switch. And this is the end of this lecture. For the next lecture, we will talk about routing in the circuit switch network and also the packet switching network. Thank you.